video is going to discuss Hess's law. So Hess's law applies when we have a chemical reaction that occurs in multiple steps. Each of the steps in the series is then going to have its own chemical reaction and therefore an equation. That equation will also have a delta H or enthalpy value associated with it. Now Hess's law states that when you add the equations in the series together, they will add up to equal the overall chemical equation for the reaction. So it would also seem appropriate that when you add the delta H's of all three reactions, then you would also be able to calculate the overall delta H of the reaction. So let's take a look at an example here. We have three reactions and they are color-coded. The first one is N2 plus 3H2 gives you 2NH3. That has a delta H value of negative 115 kilojoules. The second equation is right below, and then we have a third one in the series. If we add all three of these reactions, they should yield N2 plus 2O2 yields 2NO2. Now, if we add these three reactions and therefore find ourselves with this net equation, it would behoove us then to think the delta H's associated with each of these reactions when then added together should also yield the delta H for this reaction as well. So how do we find N2 plus 2O2 yielding 2NO2 from these three reactions, from these three equations? Because if we find that out, then we will know what manipulations we did there, perform the same manipulations mathematically to the delta H values that correspond to each equation, and then be able to find delta H. So one good tip I have is always to circle the substances that should appear in your overall equation. So I want an N2, and there it is. I'd like one of them as a reactant. I have two O2s. I will find the O2s, and there they are. Except notice that I only have 1/2 a mole of O2, and I actually need two of them. So there's going to be some changes I have to make to this O2. Another change I need to make here is that I need 2 whole moles. I only have 1/2 a mole. So we definitely want to make some adjustments to the oxygen in this third reaction. Last of all, we need 2 NO2, and we need that as a product. So notice I have 2 NO2 and it's already a product. So my N2 and my 2 NO2 are actually not only in the right position in the equations, meaning they're either reactants or products where we want them to be, but also the number of moles is also what we want it to be. 1 N2 and 2 NO2 from the orange equation that is representing the overall chemical reaction. That means I'm going to leave delta H1 alone because I'm not going to do anything to this equation. It doesn't need anything to be done. I'm also going to not manipulate the second equation either because I want to keep 2NO2 as it is. And therefore I'm not going to manipulate the delta H that corresponds with it either. But what I do need to do is some work on this third equation because my oxygen certainly needs some work. So I'm going to go ahead and make the adjustment. The first thing I want to do is move my oxygen over from the product side to the reactant side. And when I want to do that, the only means by which I can do that is to reverse the entire equation. So notice that up here we had H2 and 1/2 O2 as products and 1 H2O as a reactant. So I'm going to make the H2O the product and move the H2 and O2 to the other side as reactants. And there they are. So by basically reversing the reaction, I also need to reverse the sign for the delta H that corresponds to this reaction. The delta H was negative 43.7, and now I have switched the sign to a positive 43.7. But we're not done quite yet because I only have 1/2 a mole of this O2, and what I need is 2 moles. So how can I change 1/2 to 2? I can multiply that by a value of 4. In order to do that, though, I need to multiply all the other coefficients in this equation by the same value of 4. If you are consistent with what you do to the equation, you can manipulate it as you like. So I'm going to go ahead and multiply all of the equation by a value of 4. So let's take a look here and see what happens. When you multiply this equation by 4, you get 4 times 1 is 4H2. 4 times 1/2 is the 2O2 we were seeking, still as a reactant since we reversed it. And then 4 times 1H2O is 4H2O. What that also means is that if I have multiplied all of the coefficients of the equation, I have quadrupled the amount of reactants and the amount of products. That means I should also quadruple the amount of enthalpy that is associated with this reaction. Since we reversed the reaction, we switched the sign from negative 43.7 to positive 43.7. And since we've multiplied this equation by 4, we should also multiply the delta H value by 4. So 4 times 43.7 kilojoules is positive 174.8 kilojoules. Last but not least, let's take a look and see what's going on here. Going back to the original problem, I have then circled or put a triangle or a square around the same compounds so that it's easy for you to identify which ones are being eliminated by what. So what I have here is 3 H2s, and I also have 4 H2s here. All on the, notice here's the arrows. On the left side of the arrows, as reactants, I have 3 H2s and 4 H2s. That's 7 H2s. They will eliminate all 7 H2s on the product side. Again, reactants can cancel the products in opposing reactions. So now I've eliminated all the H2s. Why did I eliminate them? Because I don't have them in this overall equation. Therefore, I don't need to keep them. I need to eliminate them because if it's not in this final equation, it shouldn't remain. It's not contributing to the overall delta H for this overall reaction. It's done its part here in the top, in the original delta H 1, 2, and 3s. But what we want is the overall delta H of the reaction, and H2 is not necessary for this overall reactions equation. What else is not necessary is the NH3, the ammonia. So 2 of them here in the products can eliminate these 2 in the reactants. So the triangles eliminate each other. And last of all, let's eliminate some water. 4 water molecules here in the reactants cancel the 4 here in the products in the third, and this 2 squares cancel each other out. Notice how the only thing remaining is what is in black, N2 plus 2O2, N2 plus 2O2 as reactants. No other reactants remain. The lone product, just one, is the 2NO2 that remains in the product section. That is 2NO2 gas. So what we're left with when we add up these 3 equations or reactions in the series, we end up with the overall reaction. We have also then can manipulate these delta H's as we did the reactions. The only manipulation we did here was for the third equation. The manipulations we carried out were reversal of the equation and therefore the sign of delta H and multiplying the equation's coefficients and therefore multiplying the delta H value and obtaining the new delta H value. So if the sum of all these steps in the series of reactions gives us the N2 plus O2, or I should say 2O2 plus 2NO2, if the sum of these steps yields this equation, then the sum of all the delta H's should also yield the delta H for the overall reaction. So negative 115 for delta H1, negative 142.5 for delta H2, and positive 174.8 for delta H3. Add them together and you get negative 82.7 kilojoules. That is the enthalpy value that corresponds to this overall equation. So N2 plus 2O2 to yield 2NO2 has a delta H value that corresponds to negative 82.7 kilojoules. And we know that from that sign that this is an exothermic reaction.